Announcement I wanted to make to you, and I told you that there's bonus due tonight. It's a survey, not due tonight, due Friday. So you have your bonus R problem due. That's kind of fun. You should try these R problems, and bonus can only help you. So even if you try it and you get them all wrong or get one right, that's better than not trying it at all. So you might want to try it, and it can only help you. Okay? So any questions on all that? All right, so where are we now? We are right here continuing with the binary variables and regression models. So let's do that. And we're starting chapter 14. So let me just show you where we're at here. So we're starting this, chapter 14. And so I thought maybe we've been talking a lot about, we just finished talking about interactions, and before a lot of the semester we've been talking about confounders. And I thought maybe it would be useful to make sure you understand that they're not at all the same thing. All right? And so this is a visual, but before we even jump in and look at this visual, I think we should go back to a homework problem that we did way back, homework 4. So it was way back in chapter 5 when we were talking about confounders, and I think you'll understand it better. So I just want us to look at that, and it was this problem here, where we looked at these scatter plots comparing the results of a randomized experiment versus a non-randomized experiment on this, testing the same thing. So the idea was, and this is actually a true experiment that some Stat 100 honors students who wanted to be teachers did. They went into an elementary school, a few elementary schools, and they they started off randomly in this experiment, experiment B, the children were randomly assigned to the 2 difficulty levels. Now, what were they? They were all given the same identical problems. It was just a word-finding problem. It was all the same problem, but they were either labeled super easy, they were given different difficulty ranges. So they were saying this is a super easy problem, this is a medium problem, etc., all the way up to a super difficult, but they were all exactly the same thing. Well, what we want to find out, what it was testing, and what every teacher wants to know is how to, when you say something is easy or hard, or when you say something about a problem, how does it affect the learning? What psychological impact does it have? I know for me, sometimes when people would say something's really hard, I wouldn't be able to do it, and as easily as if they said it was easy, and I think it changes depending on the person. So I wanted to get at that, okay? And I was shocked by the results. We had to discontinue the experiment because what happened was, in the randomized experiment, the special needs kids who are labeled special needs, when they got a difficult problem, even though they were all the same, they started crying. They couldn't do anything. They started crying. It was a real disaster, and we had to discontinue the experiment, even though they did really fine on it, and they liked it when it was labeled easy. And we saw the reverse effect among gifted students. If it was too easy, they said, I'm just going to blow this off. I don't care. It's just easy. And they didn't do a good job. Whereas if it was labeled really hard, they felt proud of themselves and did. So we saw this effect, but we had to discontinue the experiment. Then, when we let them choose, all the special needs kids chose the easy ones. A few of them chose sort of moderately easy. A lot of them chose, but they still did better when they chose the easiest ones, and we saw this effect still. Now, this is exaggerated. I wanted to make it very dramatic. So what's the conclusion? This is what I want to say. Which one would we really trust? We have to make a decision as a teacher. We have both special needs and gifted children, often in the same class. We have to make a decision about what to do. And so this is why I want to, in which one of these, here the decision. when it was a randomized experiment, the decision was what? Overall, students did about the same, right? Whether there was no effect on whether they were labeled difficulty, labeled easy or hard. And that was because these gifted students and the special needs students basically canceled out. So if I was a teacher, I'd say, well, it doesn't, labeling difficult or hard doesn't really matter. It's going to help some students and hurt others in different, it's going to be different for different groups, but overall, the average nothing really changes. Whereas if I looked at just this, I would conclude, and this is what people thought we should do looking at this, because this experiment went on for longer because kids were allowed to do it, and they said, whoa, it helps everybody. Let's do it. Overall, it's a very good thing to do. But that's only because of the confounding. This is confounding. The idea is this. Think of polling. Think of when we have an election, right? We might have a very close election, right? But that doesn't mean that every subgroup voted the same way, right? It may be like, just think of it as a close election, 50-50, so but maybe one group was overwhelmingly for one candidate and another group was overwhelmingly for another. Those are the subgroups, but this still gives an accurate portrayal of the overall result of the experiment. Do you see what I mean? Of the election, right? You can get a 50-50, very, very close election. That doesn't mean that all the subgroups, it would be very close within each subgroup, does it? It doesn't. Look at this. We had a very, very close election between Trump and Hillary. That doesn't mean if you look at, for example, college students, it was close. Or if you look at, it wasn't. Within certain subgroups, certainly it was not close at all. But overall, it can be close. Do you see what I mean? So the overall result is valid still. But look at this. If there is confounding, what it would mean is that it was the election would have been completely swayed towards one group, maybe, even though just because it misrepresents, it ignores this group altogether. And it's just because of the placement of these groups it's an artifact of the group membership. It's confounded by group membership. It's a wrong conclusion. Whereas interactions they don't make your conclusion wrong. They when you look overall, you might not see them. But that doesn't mean, and that's why you have to include interaction terms in your model. But confounders are just mixing it up, and you want to get rid of them. You want to get rid of them. Through randomized experiments will get rid of them, including them as independent variables in a model will get rid of them. But you have to be clear about what you're doing, and so that's why I thought this might help you understand it now. So when we look at a scatter plot, maybe a good visual would be, let's look at this now. And what's messing things up and making it confounded is that these two groups, they were gifted and special needs before this happened. They're existing groups. They have different X averages, right? They have different X averages. So it's confounded because the treatment and the control group, you could say the labeled difficulties or whatever, are this X, what we're trying to figure out, is also, it's also a difference between these two groups. So they have different, whereas here they don't have different. When they were randomly assigned, they're no more likely to get the easy problems than the hard problems, and the X average is going to be the same for this group and this group. The Y's are different, of course, but the X's are the same, whereas here, the X's are different. So to have confounding, it means that the groups are, the treatment and the control group are different to begin with, okay, in terms of the X variable. You're wondering if X causes Y. That's what we're wondering. Does X cause Y? but you're getting the groups mixed up with the x's here. So that's one thing. And then the other thing to check for is the overall. They might have different slopes here, but the overall slope should be the average of the two group slopes. And here, obviously, it's not the average of the two group slopes. All right, let's do an iClicker question on just this one, and let's see if you can get it. So now, which plots have interactions? Do you remember what an interaction is? What indicates an interaction? I told you do you remember? Remember, it's different what? Slopes, within group slopes. That's it. That's what an interaction means. The effect of x on y is different for different groups. So it has different within group slopes. So choose one of those. So it's pretty easy to spot interactions. So it's just the effect of x as you go up in difficulty, effect of x on y. Is it different for the two groups? That means it has an interaction term. That means there's an interaction. Okay, so we'll just go to a minute and then we'll stop it. Okay, and the answer is they both have interactions. Yeah, very good. Okay, so let's look at that. Because the two groups have different slopes at C. See, this group and this group have different slopes, and this group have different slopes. So there's an interaction term. All right, so now let's look at the next question. And in which plot is the overall regression, this overall regression, confounded by group membership? We just talked about that, but might as well deal with the problem too. Okay, so I'll stop it. So everybody had a chance to vote. We'll stop it at a minute again. Sorry, I got ahead of myself. Okay, so I'll stop it, and the answer is what? Which plot? Just this one is confounded, plot 1. So let's look. Pretty good, not great. So let's look at this. This is difficult stuff. It's only plot 1 because the two groups in plot 1 have both different x averages, and the overall slope, this overall slope, is not equal to the weighted average of the two slopes. What would have been the weighted average of the two slopes? This one slopes down, and this one slopes up, so it would have been like that. Now this one's not confounded. The x averages are the same, and this is the overall average of the two groups. Okay, before we go to the notebook, I want to see let's see how much you've just learned just now. So I'm going to ask you another iClicker question, and this is the same as what's in your notebook. This is exactly the same as what's in your notebook. So it's the same as what we turned to, so let's just try this. Which plots have interactions? Now there's two groups. There's group A and group B, group A, B. See the two different groups? They're not marked here, but you can tell there's two distinct groups. Okay, so I think we can go just to 45. And then we'll stop it, okay? So just pick an answer. All right, we'll stop it. And let's see what you chose. So you chose D. Let's look what the answer is and why. So we'll just go down to, yeah, it is D. So plots 3 and 4, because the group slopes are different. Sorry, this is off, but here the group slopes are the same. And here they're the same, but here they're different. So that is what an interaction is. So let's just try the next one again, and then we'll explain it more carefully in the notebook. But let's just see if we can get the next one. And that's this. So now, sorry, I don't know why it keeps doing that. All right, so that's, okay, so which plots have confounders? All of them, none of them? This is a hard question. Well, I think this is too hard for you right now. Do you want to try it anyway? Or do you want to just give it a try? Okay, and then we'll see what you get. It's really hard because I didn't even show you the overall regression, but we'll go up till, why don't I give you a minute to think about it? You can talk to each other. And then we'll do it in the notebook, and I hope you'll understand it. All right, so we'll stop it. Let's see what you think. Well, Pete, you really don't know. I don't blame you. It's hard. But what did you say again? Most people, I guess the most popular answer was C, and I think that's right. Let's look at it. So let's see. Yes. Well, remember I said it had to satisfy two conditions, that you have to have different x averages. So that would eliminate this one. That has the same x average. Like this, they both groups, this group and this group has the same average. This one clearly has different ones, you know, here and here. So these three are still in the running. They could have confounders. And then condition 2, the overall slope is not equal to the weighted average of the two groups. So that eliminates this one. They're all on the same line. But this is confounded. You have two prior groups, and if you're thinking, does x cause y, it looks like, yeah, the bigger x's, the bigger y's, but within each group, there's no effect. And this one, this has the same thing. It looks like there's a positive correlation here, but if you actually took the average of the two, this has a negative slope, this has a zero slope, so the average of the two would be somewhere in between, slightly negative. And here you're saying overall it has a positive effect. So these two are confounded. All right, so let's go to the notebook and summarize that, since that this is really difficult question, so I didn't expect people to get it right away. So let's go to the document camera and go over this. And, all right, so interactions and confounders are not the same thing. So let's say we're trying to figure out if x causes y, and the data consists of these two prior groups, A and B. So these two groups, I'm sorry, I should have had these two groups, like let's say this is A and this is B, A, B, A, B, and you can see they're two distinct groups that happened first, like males or females or, right? Okay, two prior groups. And combining the two groups can give an overall regression effect that's misleading. When there's one, an interaction, it can be misleading. And what is an interaction? So or when there's a confounder. So an interaction is when X has a different effect on Y for group A than it does for group B. So you have non-parallel within group slopes, okay? So the group slopes are not parallel group slopes. The slopes aren't the same. All right, so that's what you answered first. Let's just look at interactions here. So what are we talking about? The slope looks like there's, this is X and that's Y. So the slope here is pretty flat, they have the same group slope. So let's, for each one, let's say, okay, interaction, confounder. Interaction, let's just say yes or no for each one. Interaction, confounder. Let's start with interaction because it's much easier. So interaction and confounder. Okay, so for this one, do you see how there's no interaction? There might be a confounder. For this one, again, they have parallel slopes. What I'm saying is that the effect of X on Y, this is X on Y, is the same. X seems to have no effect on Y, and X seems to have the same effect. So there's no interaction here. But here, it's clearly there is an interaction because X has the opposite effect on Y for these two. So for sure there's an interaction here, and same here because these are not parallel. Those two slopes are not parallel. Does everybody understand that? So this is an interaction. So it has different slopes. So an interaction right here, different slopes for within the groups. All right, I think you did much. Any questions on that one? So that's the interactions. But now what about confounders? Confounders, and we talk about confounders when we talk about causation. It's a difference between the A and B that's influencing both X and Y, that's changing both X and Y. And you can think of it as these two conditions have to be satisfied. The first condition is that this is the first condition here, different X averages for the two groups. So that's number one, that's the first condition. Different X averages for the two groups. So what do I mean by that? I mean, like, do you see how this X average is different than this X average? They're two different points. This has different X averages. The midpoint in the X direction of the A's in the X direction is the same as the midpoint for the B group. They have the same X averages. And this one, of course, has different X averages. I'm not talking about, I'm just saying where they fall here. These fall this, okay? So that's the condition number one. And the condition number two is this, that the overall slope is not equal to the weighted average of the two group slopes. So what do I mean by that? This is number two. Okay? So, like the overall slope. Well, what would be the overall slope here and the weighted average? First, let's just do the overall slope. Do you see how the overall slope, when you do a regression, it would almost treat these like 2 points. And the overall slope is going to be, I'll do this in pink so you can see the difference. The overall slope would be like that. Do you see why? Do you see why that would be the overall slope? Do you know what I mean? Do you want me to show you, like, just show you how it works, like make up a, I'll show you what I mean. Let's go to the data program, just because it's fun. So if we go to the data program, and and you can do this on your own. You don't have to go to scatter plots. Let's just do a blank plot. Okay, so let's just look at this. All right, so let's just simulate that first. Let's just pretend like, okay, so you have two groups, and let's just put some points down here. So let's just say this is group A, Let's try to make sure, let's see, it has no, down here we just want it completely flat. That's pretty good. Okay, so there's no correlation there. Now, let's put a group B up here, and you can see what the regression line looks like, just pretty flat. I can make it even flatter. Whoa, I didn't want it to be that, but you can make it so that it's... Okay, so that's group A. Now watch what happens just because I'll place a group B. Like if I put a group B up here, it's not gonna affect that. They're not gonna have different X's. But if I put the same thing here, and of course if I put a group B that looks the same way, they're not gonna have different, the overall slope will just keep there. But what if I put it up here? Look what happens. See, all of a sudden, we've got this really strong correlation that's completely bogus because it's not reflecting either group. Do you see what I mean? And I'm drawing it like this because it's so obvious. But when you see the data, it's not going to be so obvious like this, but that will have the same effect. There'll be overlap between the two groups like we've seen in our examples. So this is confounding. Does that make sense? All right. So now let's look at, let's go back to the, let's do a different one. So we'll start over. So now let's look at something, let's go back to the document camera so we can do each one of them. All right. So the overall slope is not equal to the weighted average. So what would be the weighted average? Let's make that a different color so you can see. The weighted average would be this. Okay? Those two are not equal, so there's confounding. Does that make sense? Both those conditions are satisfied. Satisfied, number one, different x's. And these two are not the same. So that is going to have confounding. And what you're going to conclude, you can see, you're going to erroneously conclude, if you didn't know better, that there's a positive correlation between x and y when it's not true for anyone. It's not true for A or B. It's just phony. It's confounded. It's not the average of them. It's nothing. It's just wrong. Okay, does everybody understand that? All right, how about this one? Well, this one certainly has condition one is different x's, different x averages, so it could be confounded. But when you look at the overall, what would the overall be? Doesn't that look like the overall would just be like that? And doesn't that would be the average of the two, too? I mean, that looks like they'd be the same. So there's not confounding there. Right? This is our key. So this is the overall regression line, the overall slope, and this it would be the weighted average of the two group slopes. And when they're not the same is when you can have confounding. Now here they're here and they have to have different x averages too. Okay, how about this one? This one, where's the, oh, they have different x averages, so that's okay. And now, what would be the overall average? What do you think the overall average would be? Do you think it would be that? Like if we did it, let's just say that's what's going to come up with. What do you think the overall average of something like that's going to look like? Let's try it. So let's go to our data program and see. So one of them slopes down. Let's just make a negative. This is group A's, negative like that, right? See, there's the regression line. It's negative. Okay. Now, I want one that looks like up here, that's just completely flat. And what do you think this is going to do? See what I mean? So even though there's a 0 correlation up here and a negative here, because of the placement of the, it's just going to see this is basically one cluster here, and this is so far away as another cluster of points, and it's basically just sees a positive correlation. That's what the regression line is going to do, and it has a very strong positive correlation. Does this make sense to you? And it's confounded because it's not true of either group. It's just an, And basically, this group membership is mixed up with the X's here. So if this group membership had happened first, like males and females, or those kids labeled as those kids being gifted or special ed, if it happened first, well, then it's not X that's causing Y. It's that group membership that's driving both of it. Of course, if it was a result of X, if X, but it's not in these cases. Okay? Any questions on that? So let's go back to the document camera, and all right, I think you're getting it now. So now we'll look at this, and so we saw that the overall is going to look like this, but the weighted average of the two is not. It's like that, so that's confounded, and that's both. All right, and this one we just saw. Okay, so this one, if you do something like this, I'll show you what will happen. Let's just do it. So what would the regression line do if we do something like that? Let's start over. And we have something that's very strongly positive. And then we have something that's just going to look just the same way. If I drew it right. Do you see how they're going to cancel out if I drew it exactly right here? Do you get that idea? They'll just cancel each other out. And that's also the overall weighted average. So it's not confounding. It just doesn't. This is going to happen. This is what I'm okay, let's go back to the document camera. I don't want to get ahead of myself here. So basically, the overall is the same as the two weighted averages. So when we're doing this right here is only interaction. So these two were confounded. All right, and the reason why, well, it's a lot of my brain right now because I'm doing, you're involved in this experiment between the online and the in-person class, looking at everything the same, but there could be confounders because I didn't randomly assign you to the in-person or to the online. There's confounders. I'm trying to get at what the confounders are. I mean, you guys in the in-person did significantly better on exam 1. Kind of the opposite of what happened when we were doing Stat 100, where the online people did significantly better. So we're trying to figure out what's going on and what the confounders are. And it's really fascinating what we're finding. The two, Stat 100 and Stat 200 are really different populations, even though a lot of people from Stat 100 are taking Stat 200. But we're finding opposite things. Like remember I asked you, do you like math? Okay, in Stat 100, overwhelmingly, it was really the people in the online class liked math a lot better than the people in the in-person. Here it's the opposite. So is that a confounder? The people who signed up for the in-person like math better. I can show you this data later when I put it together. But so there's a lot of there's differences. There are people. Okay, the people in the in Stat 100, the in-class people have a much higher percentage of females. It's opposite in 200. We have a higher percentage of there's a higher percentage of males when you come in the in-class. So there's a lot of different things that are going on. Now those we think are confounders, maybe because it's not like you were in one class or another and it caused you to be male or female, or it caused you to I think these are or prior things that, there are differences in the groups that are confounding it. So we're going to try to get rid of all those confounders. And if I could do a randomized experiment, I wouldn't have to deal with this. It would be so wonderful. Because there'd be the same proportion of males and females in both groups. There'd be the same proportion of people who like math and both. You know what I mean? Within chance error. So then I could get at if there's anything that's causing people to learn better overall in one or the other. So I can't do that without a randomized experiment, but by modeling, I'm going to try to get at it. Get rid of the confounders. What's my next step? My overall goal, which I'm much more interested in, the whole point of this is I believe that different groups of students learn better in different formats. And I want to help get evidence to show which groups learn better in one format or another so we can do educated guidance, educated advising for people so we could help you and say, hey, this group of students seems to perform better in, those would be interactions. Interactions, that the effect of having an online delivery versus an in-person has different effects on different types of students. Those are interaction terms. And that would be phenomenal if we could get at that. If we could figure out, and that would be great for you. You'd have some evidence-based advising. And you wouldn't just, because we all know that it's great to do what you want to do and have, of course we want you to select whichever class you want to be in, but you'd like some information about that. And so that would be so cool. So that would be interaction. So they're very, very different in the way that you, whenever you want to make anything better, like if you're a doctor, a teacher, whatever, you want to change things for people, make them better, this is what you have to think about. Okay? So I just want to give you an idea. They're both very confusing, but they're confusing for everyone. It's phenomenal if you get or even able to answer those questions before we went over them too much on the power iClicker. I really give you kudos for being able to do that. Okay, so now, and hopefully everybody understands it better now. Okay, so now we're just going to do this for the rest. This won't take long. We're going to get out early again. We're just going to look at interaction terms in the simplest context, two binary predictors. So two binary predictor explanatory variables, two x variables, and a quantitative response variable that's also known as something called two-way ANOVA. Okay, so we haven't talked about that very much, but we will later. But that's what it's called. So let's just skip this example. It's just intuitive, and I don't think it's very helpful. So let's start with this example, too. So suppose subjects were divided. There's a lot of typos here. There weren't in my old version. Something happened on this page. Okay, suppose subjects were randomly divided into 4 groups. You had only a drug A, drug B, only a drug B, both, and neither. And then you were measuring how long some disease lasted, right? So the tables below give the mean response for 3 types of models. And so we're measuring the duration of the disease is the quantitative variable, and then you have drug A coded 1 if given, 0 if not. Drug B, that's X2, 1 if given, 0 if not. I'm sure you've heard of interactions in terms of drugs all the time. You're probably advised to, on any, if you ever look at the fine print on these drugs, they'll say don't mix it with something else because it could have a bad effect. So either one of the drugs could be okay on its own, but when they're combined, they have a bad interaction. Or the reverse can happen. You can have a, the drugs can together work better than the sum of their parts. So I'm sure you've all heard of that in drug interactions, right? So they can work positively or negatively, or sometimes there's no interaction, so the effect of one drug doesn't change depending on whether the other drug is there or not. And that would be parallel slopes and no interactions. So it's just a very easy way to visualize these slopes because it's just a very, very simple model. So let's just look at these. So you can have what's called just the plain additive model, where the effect of the 2 drugs equals the sum of their parts, and there's no interaction. There's no change, okay, when the 2 are given together. So let's say this is the equation. So the duration of the disease, how many days it lasts, y, is equal to 10, so it lasts 10 days with no drugs. Then you give drug A, and it reduces it on the average by 4 days, and then drug B reduces it by 2. And together, you just add those, it would reduce it by 6, right? So here's a little chart, and so drug, the way you can read this is, okay, so here, you just have no drug B at all. So it reduces it, or just give drug A, reduces it by 6. If you look down here, A is 0, right? So 10 minus 2 is 8, right? So here, going from here to here, you're just minus 4, because you're going from A equals 0 to A equals 1, no B, right? So you get 6. And here, 10 minus 2, in this whole column, there's no A. So just read that part. 10 minus 2, when drug B is present, you put a 1 in there, and you get the 8. All right, and then this is just a simple additive effect. If you take drug A, you reduce your days sick by 4, and then now you add drug B, and you reduce it by 2 more, and you get down to 4. Okay? So 6 minus 2 is 4, or 8 minus 4 equals 4. Basically, right here, you're just putting a 1 in. Here, you can just read it as, in this square, you can just say, okay, you put a 1 in for drug A and a 1 there, so you just have 10 minus 4 minus 2 minus 6. They just add up. Okay, equals 4. That's what you get. And if you wanted to graph it, I mean, to show you the parallel slopes, you could do a graph. And we're with 3 variables, so I don't want to, I'd have to have a plane. I'm just going to graph whether drug A here is present or not. Okay, and this will be y, the number of days. So the number of days that people are sick on the y. And then I'll just do for if B was equal to 0. So you start off with nothing. This is 10, right? And then you just have, and pretend B is 0, right? And what do I get? I'll reduce it to 6 by just taking A. So for going from 0 to 1, right here, let's say that's about 5, that would be 6. So that's 6. And when it's just going to be a line, and this is when B is equal to 0. Right here, you reduce by 4 days, and you get 6, okay? Now, parallel lines would be, okay, the effect of A reducing by 4, minus 4, is the same. It's going to be a parallel line whether you have B or don't have B. So when B is present, B is equal to 1, you get this 2-day reduction when A is 0. And now you're just going to have this parallel line. It's going to say 8 minus 4, and it will take you down to 4. These 2 lines are parallel. So the effect of A is still 4, a reduction of 4, whether B is present or not. And I could have done the same thing and gotten 2 parallel lines with the slope of -2 if I'd put B here. It's the same thing. So anyway, so you have parallel slopes. That's the idea. So the effect is the same. So you start, okay, you give a person, it doesn't even matter which order, you give a person drug B, they go down, it reduces their sickness by 2 days, then you give them drug A by another 4 days, and you get to 4. So this is a simple additive model with no interaction term. Now, if you want to put an interaction term, you have to put this multiplicative. This is an interaction term, this multiplicative effect. All right? So now you're going to have the effect of the 2 drugs combined is better than the sum of the individual effects. Okay, so instead of just having an additive model, sometimes like the 2 drugs together have a synergistic effect. They do more than the sum of their parts, so it's going to reduce it more. Either one alone still does the same thing. And sorry, this is a typo here. It says no drug. It's the same as here, but somehow the publisher's messed up, okay? And this should still be ton. I wanted to keep everything the same. I'm sorry about that. And now, let's say it was, I'm just going to give you, I was going to have you come up with your own, but let me just, okay, so it's going to bring it down further. Let's say I said -3. All right, I have to give you some number here if you want to fill this chart in. So let's just say it's -3. All right, so it's going to bring it down further. When they're both present, you're not going to just go down 4 when you get A, and go down another 2 when you get B, but we're going to go down another 3, down to 1 when they're both present. You're going to have a better effect in terms of reducing the number of days you're sick. So we can do the same thing. So how would you read this? Again, look here. This is when they're both 0. So when drug A, put zeros in for drug A, so you'd have a 0, 0, 0, and you get 10. That's where that 10 is coming from, right? Now, if you just have drug A, that means 0 for B, 0 for B, you're right here. So we're at the same exact place. So you have 10 minus 4, because A becomes 1 here, and now you get the 6. All right? And now when you go this way, I'm just saying, okay, sorry about this. This says no drug B, and this says, yes, you have a drug B. But we still don't have, let's just look at this column. We still don't have drug A. So drug A is 0. So that's all 0. And now we just have 10. And when you take drug B, it goes down by 2 and you get 8. And if it wasn't for this effect, we'd just say what? 10 minus 4 minus 2, you'd have 10 minus 6, and you'd have a 4 again. But now we want to go down 3 more, so if it's 1, put a 1 in for each of these, 1, 1, and 1. So now you get 10 minus 4 minus the 2, but also minus 3, and here we get the 1. Okay, and so when we graph it, you can see that it's not parallel slopes. So you have the same, this isn't, it's just, I'm just trying to show you in the simplest context. So this is A again. This is when you go from 0 to 1. Again, this is your Y, the duration of number of days, and we start off at 10. When you have neither A nor B, and when just B equals 0, you're still just going to go down, let's say that's 5, you're still going to go down to 6 here. So that's when B equals 0. Right? And now, when A was 0 here, you're still going to start and just have B. Now B's 1, you'll start off at 8 again. But now, instead of going down to 6, you're going to go all the way. You're going to go down, you went down 2. And now you're not only going to go down 4, you're going to go down further. You're going to have a steeper slope all the way. That's supposed to be a much steeper slope. That's not supposed to be parallel. That's all the way to 1. So those are non-parallel slopes. That's a steeper slope. Okay? And the same thing we can do here. Now we can say, okay, the effect of the two drugs combined is worse. It's worse. It's going to prolong your disease. Let's say it's going to give you 7 more days. Don't take them together, even though it's going to reduce it by 4 here. So you go from, all right, so you go from 10, still going to reduce it by 4 down to 6, right? I'm just following that. Or if I was in the cat where I don't have A, I'd say 10 minus 2, and it's still going to take me to 8. But now it's going to make it so much worse, because I'm going to have, if I put 1s in here, I'll say, okay, so I start at 10, I minus 4, minus 2, but now I have to add 7. So that takes me up to 11 with the interaction. So that's worse than to begin with. That would be a bad interaction. You're better off taking no drugs. You'd be better off taking no drugs than that. So you'd have the same picture. It would be 10 here and 8. And when you have, this is 0 and 1. And this is your A. And again, that would be 6. So that's not going to change. That's when B equals 0. But now when B equals 1, even though I go down, excuse me, that's when B equals 0. But now when A and B are both, okay, when B equals 1, this is B This is going to be b equals 1. I'm just going to draw a line here. But instead of, okay, so it goes down by 2 when I take b. It's not going to go down by 4 when I take a. Instead, the two together have a bad effect, and I end up way up here when I take both of them at 11. So that you can really see is not parallel slopes. So the idea is this. These interactions give you these non-parallel slopes when they're both present, like it's both present up there. It's not, when they're both there, you're not going to get just the same thing. So that's the idea. How about any questions on that? So I think, why don't you, do you want to just work on this page together with, yes? Oh, good question. Where did I come up with that 7? These here. In the next version of the notes, this was given. And this has to be given. I was going to have you come up with like a number and do different ones, but these are both given. Okay, so don't get confused. Because when we go on the next page, I'm going to have different ones blank. Like, very good question. Thanks for asking that. Because when we go on this next page, I'm going to say, okay, and you can start these. I'll give you a few minutes to do this. Let's read them together. Suppose A and B are two treatments designed now to boost scores on some exam. Coded 1 if given, 0 if not. The numbers in the table indicate the average boost from each treatment by itself, from both together, and from neither. Fill in the blanks to make the model and the data match. I don't think there's typos on this one. So, I mean, the way we can just start off doing it together, this tells you what? That when you want to fill in this blank right here, and that's when A and B are both 1. So just put 1s in for both of them, and you get 50. And you can see there's no interaction term. When A, you add 20, and then you add 30, and you get 50. Now there's an interaction term here. You didn't get 50, so what must the interaction term be here? How would you get 60? When you have, again, look here, you have A and B are both 1. So you have 20 plus 30 is 50. Plus, what did you get? 10. You have to have 10 to equal 60. And then that will work when A and B are both 1. Okay? So try these. Just look at what square you're in. And like, for example, when you're in this square right here, that means A and B are both 0. So make them both 0. What has to go in there? When they're both 0 to make this work, that has to be a 2. And now say, okay, here, I'll just do this last one, this one for you, and then I'll let you do the rest. So when B equals 0, that means there, that's 0, right? What has to go in there to make this one true? That's the effective, that has to be 6. And this one says when A is 0, what's the effective just B? And that's 8. And that will match up. So then when you put A and B together, there's no interaction. You just add 6 and 8, and you get 16. Okay, so I'm going to let you work together and just give you a few minutes to do these, and then we'll just fill them in together. And then you'll be set to do your homework, pretty much. It's posted now, and it's due Monday. And allow yourself a little more time, I think, because you have to use the data program on the first problem. So I give you instructions on how to use it, but I think you will want to look at it and play around with it. So allow yourself a little more time for the homework. It's not due till Monday. Okay, so let's see how we got these answers here. And let's look at this. And so for this one, for example, what did we do? Well, this was blank here. So, and you can see in this square, you want 1 for A and B. So that's 5 plus 20 plus 30 is 55. So here, what did we do? Okay, so for this one, again, 1 for B and 1 for A. So put 1s in everywhere, and you get 20 plus 30 is 50, minus 10 is 40. So now let's look at this one. And how did we fill this in? All right, so you want to fill in this blank when A and B are both 0, and that was 10. Now, when you go from 10 to 12, you just add 2. And B is 0, so we're right here. So we say 10 plus 2 is 12. That's what you fill out in the 2. Now, how do we get this 5? Well, it's the same thing. Here, you're in a situation where, look at this square here. A is 0, and B is 1. So A is 0, that means these two. And now you say you want 10 plus 5 to be 15. And this last one, to get 9, well, you're putting a 1 in for both A and B. So you have 10 plus 7 plus what equals 9, and that's where the negative 8 comes. And here's the same thing. Right here, when everything's 0, you get 10 there. You add, when B is 0, you add 2 to get A. When A is 0, you add 5 to get the 15, right? And now you want to get 20 there. So you have 10 plus the 7 already, plus what equals 20, so that's 3. All right, that's it, and you should be able to do your homework. And next time we're going to start multiple regression with 2 quantitative predictors next week. So I just want to advise you to start your homework a little bit early because you're going to be using the data program for one of the problems. So the sumo wrestler problem. So be sure to just with any new program, it might take you, you might have some computer glitches. So just be sure to start your homework that's due Monday early. Okay, bye-bye. Have a good weekend.